Nuclear fusion, often hailed as the holy grail of energy production, holds immense potential for space propulsion. And its principles are fascinating. In the core of stars, fusion occurs when hydrogen nuclei combine under extreme pressure and temperature, resulting in helium and releasing vast amounts of energy. This process is what powers our Sun, providing the energy that sustains life on Earth. Scientists are now exploring how to harness this process for spacecraft, aiming to achieve efficient propulsion systems that could enable humans to explore distant planets and beyond. One of the most exciting aspects of nuclear fusion for space travel is the possibility of near-light speed travel. If we can create a reactor that reliably produces fusion reactions, spacecraft could potentially reach speeds that would significantly shorten travel times across our solar system and even to other star systems. This leads to the tantalizing question of how fusion propulsion systems might work in practice. Various designs have been proposed, including the fusion rocket, which would use the energy from fusion reactions to heat a propellant like hydrogen, expelling it at high speeds to generate. This could allow for continuous acceleration, a feature that conventional chemical rockets cannot provide. Another intriguing aspect of nuclear fusion in space is the fuel source. The primary fuel for fusion is isotopes of hydrogen, namely deuterium and tritium, which are relatively abundant. Deuterium can be extracted from seawater, while tritium can be bred from lithium, which is also available on Earth and potentially on the Moon or asteroids. This raises the question of sustainability and availability of fuel for long-term space missions. If we can establish fusion reactors in space, using these abundant fuels could drastically reduce the amount of material we need to launch from Earth, making deep space exploration more feasible. However, achieving controlled nuclear fusion on Earth has proven to be a monumental challenge. With scientists making progress through projects like ITER in France, this international collaboration aims to create a functioning fusion reactor. And if successful, it could pave the way for similar technology to be applied in spacecraft. The challenges of developing nuclear fusion propulsion extend beyond just the technology itself. There are also safety considerations to keep in mind. Unlike nuclear fission, which produces long-lived radioactive waste, fusion produces minimal waste, and the primary byproducts are typically harmless. However, there is still concern about the potential for accidents, especially if a fusion reactor were to malfunction in space. Engineers must design systems that can operate safely, even under the harsh conditions of space travel. Nuclear fusion, a process that powers the stars, including our own Sun, is the merging of two light atomic nuclei to form a heavier nucleus, releasing a tremendous amount of energy in the process. This reaction occurs under extreme temperatures and pressures, conditions that are typically found in the cores of stars. In the case of the Sun, hydrogen nuclei combine to create helium, releasing energy in the form of light and heat, which is essential for life on Earth. Scientists have long sought to replicate nuclear fusion on Earth, aiming to harness its potential as a clean and virtually limitless energy source, which could help address the growing energy demands while minimizing harmful emissions. One of the most significant challenges in achieving controlled nuclear fusion is the need to create and maintain the extreme conditions necessary for the reaction to occur. For fusion to take place, temperatures need to reach about 15 million degrees Celsius, which is approximately 10 times hotter than the core of the Sun. To achieve these high temperatures, researchers use powerful magnetic fields to confine a hot plasma, which is a state of matter where electrons are separated from their nuclei. This process is known as magnetic confinement fusion, with devices like tokamaks and stellarators being at the forefront of research. Another method, known as inertial confinement fusion, involves using powerful lasers to compress small pellets of fuel to achieve the necessary conditions for fusion. The National Ignition Facility in California is one of the leading research centers using this method, aiming to create a self-sustaining fusion reaction. Despite the technological challenges, recent advancements have shown promising results, bringing scientists closer to the goal of achieving net energy gain from fusion reactions. Countries around the globe are investing in fusion research, with notable international collaboration on projects like ITER, the International Thermonuclear Experimental Reactor, being built in France. ITER aims to demonstrate the feasibility of fusion as a large-scale energy source, and is expected its experiments in the coming years. By demonstrating that fusion can produce more energy than it consumes, ITER will pave the way for future fusion power plants. The potential benefits of nuclear fusion are immense. Unlike fossil fuels, fusion produces no greenhouse gases and generates minimal, long-lived radioactive waste. Furthermore, the fuel for fusion, such as isotopes of hydrogen like deuterium and tritium, is abundant and can be extracted from water. This means that fusion could provide a sustainable energy source for generations to come, significantly reducing our reliance on fossil fuels and contributing to the fight against climate change. Nuclear fusion, which is the process that powers the stars, including our own Sun, occurs when two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. This reaction typically involves isotopes of hydrogen, such as deuterium and tritium, which under extremely high temperatures and pressures overcome their natural repulsion due to their positive charges, allowing them to fuse together. The fusion process in stars is a natural occurrence, where the immense gravitational pressure and heat within a star enable this reaction to take place, resulting in the conversion of mass into energy, as described by Einstein's famous equation E = mc². In contrast, Nuclear fission is the splitting of a heavy atomic nucleus into two or more lighter nuclei, along with the release of energy, neutrons and gamma rays. This process is typically initiated by bombarding the nucleus with a neutron, which causes... While fusion occurs in stars and has the potential to provide a nearly limitless and clean energy source, fission is the reaction used in nuclear power plants on Earth, where uranium or plutonium isotopes are commonly used as fuel. The key differences between fusion and fission lie in the processes themselves and their respective energy outputs. Fusion, while it releases more energy per unit of mass than fission, requires very high temperatures, often in the millions of degrees Celsius, to sustain. This makes it a challenging process to harness for human use, as creating and maintaining those conditions on Earth is technologically demanding. On the other hand, fission can be achieved at much lower temperatures, thus making it easier to control and utilize in power generation, which is why it is currently the dominant form of nuclear energy production. However, fission also has significant drawbacks, such as the production of long-lived radioactive waste and the potential for catastrophic accidents as seen in historical events like Chernobyl and Fukushima. In recent years, there has been a growing interest in developing nuclear fusion as a clean energy alternative, with research initiatives like ITER, the International Thermonuclear Experimental Reactor, which aims to demonstrate the feasibility of fusion power on a commercial scale. Scientists and engineers are working on various approaches, such as magnetic confinement, which uses powerful magnetic fields to contain the hot plasma needed for fusion, and inertial confinement, which involves compressing fuel pellets with lasers or other means. Conditions for fusion. The hope is that, if nuclear fusion is considered a potential source of propulsion for space travel due to its ability to produce vast amounts of energy from relatively small amounts of fuel, which could revolutionize how we explore the cosmos. Unlike nuclear fission, which splits heavy atomic nuclei, nuclear fusion combines, like those of hydrogen isotopes, to form heavier elements, releasing energy in the process. This reaction is the same process that powers the Sun, making it a promising candidate for propulsion systems in spacecraft. The energy output from fusion reactions is millions of times greater than that of chemical reactions, such as those found in conventional rocket fuels. This means that a fusion-powered spacecraft could achieve much higher speeds and travel longer distances than current technologies allow. One of the most fascinating aspects of nuclear fusion is that it has the potential to provide a near-limitless supply of energy. If we could harness fusion effectively, we would use isotopes like deuterium and tritium, which are relatively abundant in sea. This availability is a significant advantage over traditional rocket fuels, which are finite and often require extensive extraction processes. Additionally, fusion produces minimal radioactive waste compared to fission, and the waste that is generated has a shorter half-life, making it safer for both humans and the environment. Researchers are exploring various forms of fusion propulsion, including concepts like fusion rockets, which would utilize the energy released from fusion reactions to produce thrust. For instance, a fusion rocket could potentially use a magnetic confinement system to contain the hot plasma created during the fusion process and direct the energy to expel propellant at high speeds, creating thrust. This method could enable spacecraft to reach destinations like Mars or the outer planets in a fraction of the time it would take with current chemical propulsion methods. Moreover, the idea of using fusion for interstellar travel has also captured the imagination of scientists and engineers. Projects like the Daedalus and Icarus concepts propose using fusion to propel spacecraft across the vast distances between stars. These theoretical designs suggest that a fusion-powered spacecraft could reach a significant fraction of the speed of light, opening up the possibility of exploring other solar systems and even potentially habitable exoplanets. Although we are still in the early stages of developing practical fusion propulsion technologies, the research being conducted today could lay the groundwork for future breakthroughs that will make interstellar travel a reality. In summary, nuclear fusion holds incredible promise for space travel, offering the potential for high-speed, long-distance missions with abundant fuel sources and the fusion process, which is the powerful energy source that fuels stars, including our Sun, is fundamentally based on the merging of light atomic nucleus, releasing a tremendous process. At the core of this phenomenon is the principle of nuclear binding energy, which states that when two light nuclei fuse together, the resulting nucleus has a lower mass than the sum of its parts. This mass difference, according to Einstein's famous equation, E equals mc squared, is converted into energy, making fusion an incredibly efficient source of power. In stars, the most common fusion reaction involves hydrogen nuclei, or protons, which collide at high speeds due to the extreme temperatures and pressures found in stellar cores. These conditions are necessary to overcome the electrostatic repulsion between the positively charged protons, a force known as the Coulomb barrier. When protons have enough kinetic energy, they can get close enough for the strong nuclear force to take over, which is much stronger than the repulsive force at very short distances, leading to fusion. During the fusion of hydrogen into helium, several steps occur, including the creation of isotopes Moreover, the fusion process is not limited to hydrogen. Heavier elements can fuse under the right conditions, with processes like the carbon-nitrogen-oxygen cycle playing a significant role in the later stages of a star's life. Understanding fusion has profound implications for our quest for sustainable energy on Earth. Scientists are exploring ways to replicate the conditions necessary for controlled nuclear fusion in reactors, aiming to create a clean and virtually limitless energy source. This pursuit involves significant challenges, including achieving the necessary temperatures, maintaining stability, and containing the hot plasma where the fusion occurs. Fusion research is ongoing, with experiments like the ITER project in France, which aims to demonstrate the feasibility of fusion as an energy source. The fundamental principles of fusion not only explain how stars shine, but also open doors to future energy solutions, potentially transforming the way we generate power on our planet. Throughout history, humanity's fascination with the cosmos has led to a profound understanding of our place in the universe. And this journey of discovery has unfolded over millennia, weaving together science, mythology, and culture from ancient civilizations, gazing at the stars. Astronomers using powerful telescopes. In ancient Mesopotamia, for instance, the Babylonians meticulously recorded celestial events, creating one of the earliest forms of astronomy, where they noticed patterns in the night sky, linking them to agricultural cycles and religious beliefs, while the Greeks, with thinkers like Ptolemy and Aristotle, further advanced this knowledge with their geocentric model, which placed Earth at the center of the universe, a notion that persisted for centuries until Copernicus, in the 16th century, proposed a heliocentric model, suggesting that the Sun, rather than the Earth, was at the center. Revolutionary idea that eventually paved the way for future astronomers like Galileo, who, with his telescope, made groundbreaking observations that challenged the established views of his time. The Renaissance brought about a pivotal shift as scientists began to question long-held beliefs, leading to a deeper exploration of planetary motion, and Kepler's laws of planetary motion demonstrated that planets move in elliptical orbits, a discovery that fundamentally changed our understanding of celestial mechanics. Meanwhile, in the 20th century, the advent of modern physics, particularly the theories of relativity proposed by Einstein, revolutionized our perception of time, space, and gravity, revealing a universe that was far more complex and dynamic than previously imagined. Furthermore, the launch of the Hubble Space Telescope in 1990 allowed us to peer deeper into the cosmos, unveiling distant galaxies and helping us measure the rate of the universe's expansion, providing evidence for the Big Bang theory, which posits that the universe began from an extremely hot and dense state and has been expanding ever since. As we look at the historical context of space exploration, the mid-20th century marked a notable turning point with the launch of Sputnik by the Soviet Union in 1957. The world watched as humanity took its first steps into the realm of space travel, igniting the space race, states, and the Soviet Union. This competition led to significant advancements in technology and science, culminating in the Apollo 11 mission, where astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the moon in 1969, an event that not research into nuclear fusion, the process that powers the stars, began in the early 20th century. Specifically, scientists were intrigued by the idea of harnessing the energy produced by fusing atomic nuclei, which could potentially provide a limitless source of clean energy. The groundwork for nuclear fusion research was laid by several pioneers. Among them, the physicist Hans Bethe, who played a crucial role in understanding how hydrogen nuclei fuse to form helium in stars, a process that releases an incredible amount of energy. Bethe's work, which earned him the Nobel Prize in Physics in 1967, was instrumental in explaining the mechanisms of stellar nucleosynthesis, which is the process by which stars create heavier elements through fusion. During the same period, other scientists, like Edward Teller and George Gamow, contributed significantly to the theoretical understanding of fusion. Teller, often referred to as the father of the hydrogen bomb, was involved in exploring fusion not just as a natural process in stars, but also as a potential means to create powerful weapons. Meanwhile, Gamow, a prominent physicist and cosmologist, explored the implications of fusion in the context of the Big Bang and the early universe, further enhancing our understanding of how elements are formed. By the 1950s, research into nuclear fusion began to shift towards practical applications, particularly in the context of energy generation. The development of devices like the tokamak, a type of magnetic confinement device, was spearheaded by scientists such as Igor Tamm and Andrei Sakharov in the Soviet Union. The tokamak design became one of the most promising approaches to achieving controlled nuclear fusion, leading to extensive research in various countries, including the United States and Europe, as scientists sought to replicate the conditions found in stars, where immense pressure and temperature allow fusion to occur. In the decades that followed, fusion research adapted and evolved, with various experiments and projects launched to explore different methods of achieving sustainable fusion reactions. The 1980s saw the establishment of large international collaborations, such as the Joint European Torus JET project in the UK, which aimed to investigate the feasibility of fusion as a viable energy source. Today, the quest for practical nuclear fusion continues, with projects like ITER, the International Thermonuclear Experimental Reactor, which involves scientists and engineers from around the world, striving to make fusion energy a reality, tapping into the same powerful reactions that fuel our sun, and potentially transforming the way our understanding of nuclear fusion, the process that powers the stars, including our sun, has undergone significant evolution over the decades, beginning in the early 20th century, when scientists first began to unlock the secrets of atomic energy. Initially, the concept of fusion was largely theoretical, with pioneers like Albert Einstein, whose famous equation E⁴ hinted at the immense energy released when mass is converted into energy. In the 1930s, physicists such as Hans Bethe made substantial contributions by explaining how hydrogen nuclei combine to form helium in stellar environments, releasing energy in the process, and this laid the groundwork for understanding stellar nucleosynthesis, the process by which formed in stars through fusion. As we moved into the mid-20th century, the focus shifted from theoretical exploration to practical applications, particularly during the post-World War II era, when researchers began to seriously consider nuclear fusion as a potential source of energy for electricity generation. The invention of devices like the tokamak, a type of magnetic confinement device, in the 1950s, scientists realized that by using strong magnetic fields, they could contain hot plasma, allowing for the conditions necessary for fusion to occur, although achieving the extreme temperatures and pressures found in stars remained a formidable challenge. In the following decades, experiments such as those conducted at the Joint European Torus JET in the 1980s further advanced our understanding, demonstrating the feasibility of sustaining fusion reactions for longer periods. These experiments indicated that while fusion could produce energy, the energy output was still less than the energy input required to initiate and maintain the reaction, a situation referred to as net energy gain. Fast forward to the 21st century, and our understanding has continued to evolve, particularly with international collaborations like the ITER project, which aims to demonstrate the viability of fusion as a large-scale and carbon-free source of energy. This ambitious endeavor, involving multiple countries, seeks to create a self-sustaining fusion reaction that produces more energy than it consumes, a milestone known as ignition. The technology has also seen advancements in laser-driven fusion, exemplified by the National Ignition Facility in the United States, where powerful lasers are used to compress fuel pellets to extremely high densities and temperatures, pushing the boundaries of what is achievable in fusion. Research. Today, researchers are exploring a variety of fusion approaches, from magnetic confinement to inertial confinement, and even alternative concepts like stellarators, which in the realm of space exploration. The idea of fusion-driven spacecraft, engineers. For decades, with its potential to revolutionize how we travel beyond our planet, early concepts for fusion-driven spacecraft date back to the mid-20th century, when researchers began to explore the possibilities of harnessing the power of nuclear fusion, the same process that fuels the sun, to propel spacecraft at incredible speeds. One of the most notable early designs was the Project Orion, initiated in the late 1950s, which proposed using nuclear explosions to propel a spacecraft. The concept involved detonating a series of nuclear bombs behind the vehicle, allowing the shockwaves to push it forward. Although the idea was ambitious, it raised significant safety and environmental concerns, leading to its eventual abandonment. Another intriguing concept was the use of fusion pellets in a design known as Project Daedalus, developed by the British Interplanetary Society in the 1970s. This project envisioned a spacecraft that would carry a fusion reactor capable of fusing hydrogen isotopes, such as deuterium and helium. 3. To produce thrust. The Daedalus spacecraft would be designed to travel to nearby stars, utilizing the energy from the fusion reaction to accelerate to a significant fraction of the speed of light. The engineering challenges were immense, especially regarding the creation and containment of the fusion reaction, but the project highlighted the potential of fusion energy for interstellar travel. Furthermore, researchers proposed various fusion-based propulsion systems, like the direct fusion drive, which seeks to combine aspects of traditional rocket engines with nuclear fusion technology. This concept involves using a fusion reactor to heat a propellant, which is then expelled to produce thrust. The advantage of such a system is that it could offer a much higher efficiency compared to conventional chemical rockets, enabling missions to distant planets in a fraction of the time currently required. In the 1980s, the concept of the Helios spacecraft emerged, which aimed to utilize fusion energy for propulsion while also being capable of harnessing solar energy. This hybrid approach was envisioned to allow the craft to operate efficiently, both in the inner solar system and on missions to the outer planets, demonstrating how fusion technology could be integrated into existing space mission frameworks. Additionally, other researchers have explored the concept of using magnetic confinement fusion, similar to that used in experimental reactors like ITER, to create a propulsion system. This technology would involve using powerful magnetic fields to contain and stabilize the fusion reaction, producing thrust in when we delve into the technical aspects of space and the universe. We encounter a fascinating landscape filled with complex systems, advanced technology, and intricate processes that enable our exploration and understanding of the cosmos. One fundamental aspect of space technology is the development of rockets, which are essential for launching payloads into orbit or even further into space. Rockets operate based on the principles of Newton's third law, which states that for every action there is an equal and opposite reaction. This means that when a rocket expels gas downwards, it propels itself upwards, allowing spacecraft to break free from Earth's gravitational pull. The engineering behind rocket design involves materials that can withstand extreme temperatures, pressures and forces, which makes the choice of materials such as carbon fiber composites and heat resistant alloys crucial for success. As we look at the technical aspects of spacecraft, it's vital to understand the role of avionics, the electronic systems used for navigation, communication, and control. Modern spacecraft rely on sophisticated sensors, including gyroscopes and accelerometers, to determine their orientation and velocity in space. These sensors feed data to onboard computers, which process information and execute commands, ensuring the spacecraft. Moreover, robust communication systems are necessary for transmitting data back to Earth, which involves radio waves and sometimes laser communications for higher data rates. Another key component of space missions is propulsion systems, which can vary significantly depending on the mission profile. Chemical propulsion, which uses the combustion of propellants to produce thrust, is the most common form, but there are also innovative methods like ion propulsion, which utilizes electric fields to accelerate ions, providing a much more efficient use of fuel over long durations. This is particularly beneficial for deep space missions, where carrying large amounts of fuel is impractical. When we talk about satellites, we must consider their orbits, which are determined by a balance of gravitational forces and the satellite's velocity. The understanding of orbital mechanics, which involves calculations based on Kepler's laws and Newtonian physics, is crucial for placing satellites in the right position to provide services such as telecommunications, weather forecasting, and Earth observation. In the realm of astronomical observation, telescopes represent a remarkable technical achievement. Ground-based telescopes, equipped with adaptive optics, can correct for atmospheric distortion, enabling astronomers to capture clearer images of distant celestial bodies. Space telescopes, like the Hubble Space Telescope, avoid atmospheric interference altogether, allowing for unprecedented views of the universe. The technical nuclear fusion, a process that powers the stars, including our Sun, relies on specific fuels to ignite the reaction, and the most commonly studied fuels for achieving fusion on Earth are isotopes of hydrogen, primarily deuterium and tritium. Deuterium, which is a stable isotope of hydrogen, contains 1 proton and 1 neutron in its nucleus, while tritium, a radioactive isotope, has 1 proton and 2 neutrons. The fusion of these 2 isotopes can release an enormous amount of energy, approximately 4 times more than the energy produced by nuclear fission, which is the process used in current nuclear power plants. When deuterium and tritium nuclei collide at extremely high temperatures, in the range of millions of degrees Celsius, they can overcome their natural repulsion due to their positive charges, allowing them to fuse together, creating helium and releasing neutrons and a significant amount of energy in the process. Another promising fusion fuel is helium. 3, which consists of 2 protons and 1 neutron. Although helium 3 is rare on Earth, it is more abundant on the Moon and in the atmospheres of gas giants like Jupiter. Fusion reactions using helium 3 can produce energy without generating the same level of radioactive waste as deuterium reactions, making it an attractive option for future fusion reactors. However, the technology to effectively harness helium 3 is still in the experimental stages. In addition to hydrogen isotopes, researchers are also exploring the potential of using advanced fuels like boron and proton fusion. In this reaction, boron-11, which is stable and non-radioactive, can fuse with protons to produce 3 helium-4 nuclei. This reaction has the advantage of producing no neutrons, which means it generates less radioactive waste and can be more manageable in terms of safety and environmental impact. But the temperatures required are significantly higher, making it more challenging to achieve. Understanding these fuels and their reactions is crucial for the development of fusion as a viable energy source. Scientists are working on various methods, such as magnetic confinement, in tokamaks and inertial confinement, through lasers to create the conditions necessary for these fusion reactions to occur. The quest for sustainable, safe and virtually limitless energy through nuclear fusion is one of the most exciting frontiers in modern physics and engineering, and advancements in this field could have profound implications for our energy future, potentially providing a clean alternative to fossil fuels and significantly reducing greenhouse gas emissions. Magnetic confinement and inertial confinement are two distinct methods that scientists are exploring to achieve nuclear fusion, which is the process that powers the stars, including our Sun. In magnetic confinement, the idea is to use powerful magnetic fields to contain and stabilize a hot plasma, which is a superheated gas made up of ions and electrons at extremely high temperatures, often exceeding millions of degrees Celsius. The most well-known example of this approach is the tokamak, a donut-shaped device that creates a magnetic field to keep the plasma away from the walls of the reactor, preventing it from cooling down and losing the necessary conditions for fusion to occur. The magnetic fields need to be carefully designed and controlled, as any instability can lead to the plasma touching the reactor walls, which can cause energy loss and damage to the reactor itself. On the other hand, inertial confinement works on a different principle. In this method, small pellets of fusion fuel, typically a mix of deuterium and tritium, are rapidly compressed and heated using powerful lasers or other forms of energy, such as X-rays, to achieve the necessary conditions for fusion. The idea is to create a shock wave that compresses the fuel to extremely high densities in a very short time, often just a few nanoseconds. Facilities like the National Ignition Facility in the United States focus on this technique, aiming to achieve the right conditions for fusion by delivering an enormous amount of energy in a very brief burst to the tiny pellet of fuel. The rapid compression raises the temperature and pressure to levels where nuclear fusion can occur, allowing the fuel nuclei to overcome their natural repulsion due to their positive charges. While both methods aim for the same ultimate goal of achieving sustainable fusion reactions, they rely on fundamentally different physical principles and technological approaches. Magnetic confinement seeks to maintain a stable plasma for longer periods of time, which can lead to continuous energy production, while inertial confinement focuses on achieving fusion in very short, intense bursts. Each method presents its own set of challenges. For instance, magnetic confinement requires maintaining stability over time, complicating the design and operation of the magnetic fields, whereas inertial confinement must achieve precise timing and energy delivery to successfully compress the fusion fuel. Researchers are continuously working on both fronts, exploring improvements in their respective technologies and seeking to overcome the technical hurdles that have so far prevented practical fusion energy from becoming a reality. The pursuit of fusion energy, with its potential for providing a nearly limitless and clean source of power, remains one fusion propulsion, often seen as the holy grail of space travel, requires several key technological advancements to become feasible, and these advancements are not just incremental improvements, but rather groundbreaking innovations that could change the landscape of how we explore the universe. First, we need significant developments in fusion reactor technology itself, specifically in creating and sustaining a controlled fusion reaction that can produce more energy than it consumes, a challenge that has puzzled scientists for decades. Traditional methods, like magnetic confinement, seen in projects like ITER, need to evolve, improving their efficiency and stability. And this may involve new materials capable of withstanding the extreme conditions within a fusion reactor, such as high temperatures and radiation. Second, advancements in superconducting materials are essential, which would allow for more efficient magnetic confinement systems, reducing energy loss and making it possible to maintain the high magnetic fields necessary for fusion reactions. Additionally, we need to enhance our understanding of plasma physics, as the behavior of plasma at the temperatures required for fusion is complex and not fully understood. Researchers are exploring advanced computational models and simulations to predict plasma behavior more accurately, which is crucial for developing reliable fusion systems for propulsion. Another area that requires innovation is the development of lightweight, efficient engines that can harness the energy produced by fusion reactions. This means creating propulsion systems that can convert the thermal energy from fusion into thrust effectively, perhaps through novel mechanisms such as direct energy conversion, which could drastically improve the performance of spacecraft. Moreover, we need advancements in fuel sourcing as current fusion. Experiments mainly use isotopes like deuterium and tritium, which may limit scalability and sustainability. Finding alternative fuels, such as helium-3, could open new possibilities, especially if we can source them from lunar regolith, thus enhancing the feasibility of fusion propulsion for deep space missions. Furthermore, the integration of advanced robotics and AI in managing and maintaining fusion reactors will be crucial, as these technologies can help monitor the complex systems involved and make real-time adjustments to ensure optimal performance. Lastly, the development of robust safety protocols and containment systems is vital, as any fusion propulsion system must ensure that it operates safely, especially when dealing with the immense energies involved. This includes building redundant systems and fail-safes that can handle unexpected scenarios, ensuring that the technology can be trusted for both crewed and uncrewed missions. All these advancements work together, creating a comprehensive framework that will enable fusion propulsion to become a reality, propelling humanity farther into the cosmos, unlocking the in recent years. The field of space exploration and research has been bustling with groundbreaking developments, pushing the boundaries of our understanding of the universe. And one of the most exciting areas of current research is the study of exoplanets, which are planets outside our solar system. Scientists are using advanced telescopes, such as the James Webb Space Telescope, which was launched in late 2021, to examine the atmospheres of these distant worlds, searching for signs of water vapor carbon dioxide, and other molecules that could indicate the potential for life. This research is crucial, as it helps us to understand not only the possibility of life beyond Earth, but also the conditions that allow planets to support life, guiding our search for habitable environments in the cosmos. Another significant focus of current research involves the study of dark matter and dark energy, which together make up about 95% of the universe, yet remain largely mysterious. Astrophysicists are conducting experiments using particle colliders and large observatories, such as the Large Hadron Collider in Switzerland and the Vera C. Rubin Observatory in Chile, to gain insights into the fundamental nature of these elusive components of the universe. Understanding dark matter and dark energy could revolutionize our comprehension of the universe's formation, its expansion, and its fate. As researchers delve deeper into these topics, they are also exploring the potential for new physics beyond the current standard model, which describes the fundamental particles and forces in the universe. In addition, the quest for a deeper understanding of our own solar system has led to exciting missions, such as the ongoing study of Mars through the Perseverance rover, which is actively collecting samples and searching for signs of ancient life. The rover is equipped with advanced technology, including a suite of scientific instruments designed to analyze rock and soil samples, which will pave the way for future human exploration of the Red Planet. Moreover, missions to the outer planets, like NASA's Europa Clipper, which aims to explore Jupiter's moon Europa, are being designed to investigate subsurface oceans that could harbor life, making the exploration of icy worlds a priority for astrobiology research. Another area of great interest is the development of space technology, particularly in the realm of propulsion systems. Researchers are investigating innovative technologies such as ion thrusters and nuclear thermal propulsion, which could potentially revolutionize space. Travel by reducing travel times to distant planets and making deep space exploration more feasible. These advancements could enable future missions to places like Mars or even the outer planets. In recent years, the field of nuclear fusion research has made remarkable strides, particularly in its potential application for space propulsion, which could revolutionize how we travel beyond Earth. One of the most exciting breakthroughs comes from the successful experiments conducted by the National Ignition Facility, or NIF, located at Lawrence Livermore National Laboratory, where researchers achieved a significant milestone by reaching what is known as ignition. This means they produced a fusion reaction that released more energy than was input into the process, a crucial step toward making fusion a viable energy source. The implications of this for space travel are profound, as nuclear fusion could provide a nearly limitless source of energy, enabling spacecraft to travel faster, further and more efficiently than current chemical propulsion methods allow. Moreover, private companies, such as Helion Energy and the Technologies, are also pushing the boundaries of fusion technology. Helion Energy has been working on its unique approach to fusion, which they call pulsed fusion, and they aim to create a compact fusion generator that can operate efficiently and affordably. This type of technology could lead to the development of fusion-powered rockets, allowing spacecraft to travel to distant planets or even beyond our solar system at unprecedented speeds. The technologies, on the other hand, is focused on achieving stable plasma confinement, which is vital for sustaining fusion reactions long enough to generate usable energy. Their advancements could eventually lead to a fusion propulsion system that would drastically reduce travel times to Mars, for instance. Additionally, researchers at the Massachusetts Institute of Technology have been exploring the use of fusion as a propulsion system for interstellar travel, with concepts such as the direct fusion drive. This innovative system proposes using fusion reactions to create thrust directly, which could potentially allow a spacecraft to reach significant fractions of the speed of light. Such speeds would open up the possibility of reaching nearby star systems in a human lifetime, making the dream of interstellar travel seem more achievable than ever before. The advancements in material science also play a crucial role in this research, as developing materials that can withstand the extreme conditions inside a fusion reactor is vital. Innovations in superconductors and advanced ceramics are allowing for the construction of more efficient reactors, which is essential for both energy generation and potential propulsion systems. The quest to create a fusion reactor that can operate continuously rather than in short bursts is also ongoing, with various teams around the world working on designs that could lead to practical applications in space. While there is still much work to be done in the realm of fusion propulsion research, several key organizations and institutions are at the forefront, pushing the boundaries of what is possible in space travel. One of the most notable players is NASA, which has been exploring fusion propulsion concepts for decades, particularly through its Advanced Space Propulsion project, which aims to develop technologies that could enable interstellar travel, utilizing fusion reactions to provide thrust over long distances. Meanwhile, the Princeton Plasma Physics Laboratory, affiliated with Princeton University, has been conducting significant research into plasma physics and fusion energy with a focus not only on energy generation, but also on its potential applications for propulsion in space. The Massachusetts Institute of Technology, or MET, has also made strides in this field, particularly through its Plasma Science and Fusion Center, where researchers are investigating various approaches to harness fusion energy and exploring how it might be adapted for use in spacecraft. On the international stage, the European Organization for Nuclear Research, known as CERN, plays a role in fusion research, although its primary focus is on particle physics. The technologies and discoveries made there often have implications for fusion propulsion as well, especially advancements in plasma, confinement, and magnetic fields. Additionally, private companies like Helion Energy and the Technologies are emerging as significant contributors to fusion research, with innovative approaches aimed at achieving practical fusion energy, which could eventually lead to viable propulsion systems for space exploration, making them key players to watch in the coming years. Furthermore, the National Renewable Energy Laboratory and the Los Alamos National Laboratory are also involved in fusion research, each contributing unique expertise and technology development that could be applied to propulsion systems. These organizations are collaborating with universities and other research institutes, facilitating a global effort to harness the power of fusion for various applications, including space travel, and their progress could redefine our understanding of propulsion technologies for the future. Experimental fusion reactors, which are designed to replicate the processes that power the Sun, play a significant role in advancing our understanding of propulsion systems, particularly for space travel. The principles of fusion, where atomic nuclei combine to release vast amounts of energy, have implications not just for energy production on Earth, but also for developing advanced propulsion technologies that could one day enable human exploration of distant planets. In fusion reactors, the intense heat and pressure create conditions similar to those found in stars, allowing scientists to study how fusion reactions can be controlled and sustained. This research contributes to our understanding of high-energy physics, which is essential for designing propulsion systems that would harness fusion for spacecraft. One of the most promising areas of research is in fusion propulsion, which could potentially provide much greater efficiency than traditional chemical rockets. For instance, by utilizing the energy produced in fusion reactions, a spacecraft could achieve much higher thrust to weight ratios, allowing it to travel faster. The concept of fusion-driven rockets, sometimes referred to as fusion propulsion, hinges on the idea of using the energy released from fusion reactions to propel a spacecraft. This could lead to travel times to Mars being reduced from several months to just a few weeks, which would be a monumental leap in space exploration capabilities. Moreover, experimental fusion reactors help scientists understand the behavior of plasma, which is the fourth state of matter and consists of charged particles. Plasma physics is crucial for the development of fusion propulsion systems, as these systems would need to manage plasma efficiently to harness the energy produced during fusion reactions. By studying how plasma behaves under different conditions in fusion reactors, researchers can gain insights into how to control and stabilize plasma flows, which is a critical aspect of making fusion propulsion viable. Additionally, the materials used in experimental fusion reactors provide valuable information for developing spacecraft that can withstand the extreme conditions of space travel. The intense heat and radiation produced during fusion reactions require advanced materials that can endure these harsh environments. Research in this area informs the design of spacecraft components, ensuring they are robust enough to handle not only the fusion process but also the challenges of space, such as micrometeoroid impacts and high levels of radiation. Furthermore, as experimental fusion reactors are tested and refined, they offer a platform for innovative technologies that can enhance propulsion systems. For example, advancements in magnetic confinement and laser-based fusion techniques could lead to new methods for accelerating spacecraft. The knowledge gained from these fusion experiments can also lead to breakthroughs in energy storage and conversion, which are vital for fusion propulsion, a concept that harnesses the power of nuclear fusion. Offers several exciting advantages over traditional propulsion systems. One of the most significant benefits of fusion propulsion is its potential for high efficiency, which could enable spacecraft to travel faster and farther than ever before. Unlike chemical rockets, which rely on the combustion of fuel, fusion propulsion generates energy by fusing light atomic nuclei, such as hydrogen isotopes, which releases a tremendous amount of energy. This energy output is many times greater than that of chemical reactions, meaning that a fusion-powered spacecraft could achieve much higher speeds, reducing travel time across vast distances in space, such as the journey to Mars, or even the outer planets. Moreover, fusion propulsion systems could utilize fuel sources that are abundant and widely available, such as isotopes of hydrogen found in seawater. This means that, theoretically, a fusion-powered spacecraft could refuel during its journey, making long-term space exploration more feasible. Instead of carrying large amounts of fuel, which adds weight and complexity, a spacecraft could generate its fuel from the environment, allowing for more extended missions and the possibility of exploring multiple destinations without the need to return to Earth for refueling. Another advantage of fusion propulsion is the reduced production of harmful byproducts. Chemical propulsion systems produce significant amounts of greenhouse gases and other pollutants, while fusion reactions primarily produce helium, a harmless gas. This reduction in harmful emissions makes fusion propulsion not only a cleaner option for space travel, but also potentially more sustainable, as it aligns with efforts to minimize humanity's environmental impact even beyond our planet. Additionally, the thrust produced by fusion engines could be more continuous and controlled than that of traditional rockets. This capability allows for a smoother acceleration and deceleration process, providing a more comfortable ride for astronauts. The ability to adjust thrust levels throughout a mission could also facilitate complex maneuvers, such as entering orbit around distant celestial bodies or making course corrections, enhancing the overall mission flexibility. Furthermore, the technological advancements required for fusion propulsion are likely to drive innovation in related fields, including materials, science, power generation, and energy storage. These breakthroughs could have far-reaching implications, benefiting not only space exploration, but also terrestrial applications, potentially leading to more efficient energy systems and advanced materials capable of withstanding extreme conditions. In terms of safety, fusion propulsion systems may offer advantages over traditional nuclear propulsion systems. While fission reactors used in some spacecraft carry risks associated with radioactive waste and meltdown scenarios, fusion reactions do not produce long-lived radioactive waste, significantly mitigating long-term when we look at the future of space travel. One of the most exciting areas of research is fusion propulsion, which offers several advantages over traditional chemical propulsion methods. First and foremost, fusion propulsion has the potential to provide a much higher thrust-to-weight ratio, meaning that spacecraft powered by fusion engines could accelerate more rapidly, allowing them to reach their destinations faster than those using chemical rockets. This is essential for long-distance missions such as those to Mars or even further into the solar system, where time is a critical factor. Additionally, fusion reactions can produce a significant amount of energy from a small amount of fuel, which is a game-changer for space exploration. While chemical rockets rely on the combustion of fuel, which quickly depletes and requires large, heavy tanks, fusion could utilize isotopes like deuterium and helium-3, which are more abundant and require less mass to carry on board. Moreover, fusion propulsion systems can operate continuously for extended periods, as opposed to the short bursts of thrust produced by chemical rockets. This continuous thrust could enable spacecraft to reach higher speeds over time, making it feasible to travel to distant planets or even beyond our solar system. The efficiency of fusion engines could mean that once a spacecraft is in motion, it could maintain its speed with less fuel than required for traditional propulsion systems, thereby reducing the overall mass and cost of missions. Another significant advantage is the reduction of harmful byproducts associated with chemical propulsion. Chemical rockets produce a lot of waste, including greenhouse gases and other pollutants, which can have negative effects not only on Earth, but also in space, where debris and contamination can pose risks to spacecraft and habitats. In contrast, fusion reactions primarily produce helium, which is non-toxic and harmless, making fusion propulsion a cleaner alternative for exploration. This aspect aligns well with the increasing emphasis on sustainable practices. Furthermore, advancements in fusion technology could lead to a better understanding of fundamental physics as scientists study the challenges of creating and maintaining fusion reactions in a controlled environment, particularly in the unique conditions of space. The research and development of fusion propulsion could drive innovation in related fields, leading to new technologies that benefit both space exploration and life on Earth. For instance, breakthroughs in materials science, energy storage, and power generation could emerge from the pursuit of effective fusion systems. Finally, the potential for in-situ resource utilization is another exciting aspect of fusion propulsion. As space missions become more ambitious, the ability to harness local resources, such the energy output of fusion, is fundamentally different from that of traditional rocket fuels. And understanding this difference can illuminate the potential of fusion as a power source for space exploration. Traditional rocket fuels, like liquid hydrogen, combined with liquid oxygen, provide energy through chemical reactions, which, while effective, release a relatively small amount of energy per unit mass. For instance, the energy density of liquid hydrogen and oxygen is about 13.1 megajoules per kilogram, which, though sufficient for launching spacecraft, limits the range and efficiency of travel beyond Earth's gravity. In contrast, nuclear fusion, the process that powers the sun, releases energy through the fusion of atomic nuclei, typically hydrogen isotopes, such as deuterium and tritium. When these nuclei collide at high temperatures and pressures, they combine to form helium, releasing vast amounts of energy in the process, estimated at around 17.6 million electron volts per reaction. To put this into perspective, the energy density of fusion fuel can reach approximately 100 million times greater than that of traditional chemical fuels, making it an incredibly potent source of energy. This immense energy output not only means that a small amount of fusion fuel could theoretically propel a spacecraft much farther and faster than conventional rockets, but also suggests a potential for more efficient long-duration mission, such as those to Mars, or even beyond. Additionally, the byproducts of fusion are far less hazardous than those of chemical reactions, producing mainly helium, which is non-toxic and harmless, as opposed to the greenhouse gases and other pollutants released by burning rocket fuels. This aspect of fusion not only makes it an appealing option for deep space travel, but also aligns with goals for sustainable and environmentally friendly exploration. However, despite its advantages, harnessing fusion for practical use, especially in rocketry, remains a significant challenge. While scientists have made great strides in achieving controlled nuclear fusion on Earth, such as in experiments at the ITER facility in France, creating a compact and efficient fusion engine suitable for spacecraft, is still in the research and development phase. Achieving the necessary conditions for sustained fusion reactions, including extreme temperatures above 100 million degrees Celsius, poses engineering challenges that have yet to be fully overcome. Moreover, even if we can achieve successful fusion reactions, developing a system that can effectively convert that energy into thrust is another hurdle that researchers are actively working to address. As we continue to explore the universe, the comparison between fusion and traditional rocket fuels highlights the potential for revolutionary advancements in propulsion technology. Should we unlock the secrets? Fusion propulsion, a concept that's gaining traction in the realm of space exploration, has the potential to revolutionize how we travel within our solar system, significantly reducing travel times to distant planets and other celestial bodies. Unlike traditional chemical rockets, which rely on burning fuel to produce thrust, fusion propulsion harnesses the power of nuclear fusion, the same process that fuels. By fusing light atomic nuclei, such as hydrogen isotopes, into heavier nuclei, fusion produces an immense amount of energy. Fusion produces an immense amount of energy, far exceeding what chemical reactions can achieve. This energy, when directed into a propulsive system, can create a continuous thrust, allowing spacecraft to accelerate steadily over long distances rather than relying on short, powerful bursts followed by coasting, as is the case with conventional rockets. One of the most exciting aspects of fusion propulsion is its potential for high specific impulse, which is a measure of how efficiently a rocket uses propellant. The specific impulse of fusion rockets could be orders of magnitude greater than that of chemical rockets, allowing spacecraft to carry less fuel for the same journey or to travel much faster with the same amount of fuel. For instance, while a conventional spacecraft might take several months or even years to reach Mars, a fusion-powered vehicle could potentially make the journey in a matter of weeks. This drastic reduction in travel time could open up new opportunities for manned missions to the outer planets, such as Jupiter or Saturn, which are currently daunting prospects due to the long durations required for travel. Moreover, the continuous thrust provided by fusion propulsion means that a spacecraft could maintain a constant acceleration for a significant portion of its journey. This capability would not only shorten travel times, but also improve the comfort of astronauts on board, as they would experience a steady force akin to gravity, rather than the weightlessness associated with traditional spaceflight. This could have profound implications for long-duration missions, as it may help mitigate some of the negative health effects of prolonged exposure to microgravity. Additionally, fusion propulsion could enable spacecraft to reach much higher velocities, allowing for faster rendezvous with potential targets, such as asteroids for mining, or even for returning samples from distant moons or planets. Faster travel times could also enhance the feasibility of human exploration of Mars, making it more practical to send crewed missions with shorter durations, thus reducing the risks associated with long-term space habitation. In the broader context of solar system exploration, fusion propulsion could facilitate more ambitious missions, such as multiplanetary expeditions or missions that involve visiting multiple targets when it comes to exploring space. There are many challenges and limitations that scientists and engineers face which can affect our understanding of the universe, and one of the primary challenges is the vast distances involved, as space is incredibly large, and even our closest neighbor, Proxima Centauri, is about 4 light years away, making it practically unreachable technology. This immense distance means that sending spacecraft to other star systems would take decades, if not centuries, and the longer a mission takes, the more difficult it becomes to maintain communication and control from Earth. This also raises the question of how to ensure functional over such long periods, as many components may degrade or fail over time, leading to potential mission failures. Another significant limitation is the harsh environment of space, which includes extreme temperatures, radiation, and microgravity. Human health and the functioning of equipment, for instance, prolonged exposure to cosmic radiation, can increase the risk of cancer for astronauts, while the vacuum of space poses serious challenges for human life, making it essential to develop effective life support systems. Missions. In addition, the cost of space exploration is a considerable barrier. Launching rockets, building spacecraft, and conducting research can run into billions of dollars, which poses a challenge for governments and organizations, particularly when budgets are tight. This financial tough decisions about which missions to prioritize, often putting high-risk, high-reward projects on the back burner. Furthermore, international cooperation plays a crucial role in addressing these challenges, as space exploration often requires collaboration among various nations, pooling resources, knowledge, and technology. But political tensions can complicate these partnerships. Effectiveness in joint missions. Technological limitations also present significant hurdles. Even though we have made tremendous advances in rocket technology, propulsion systems still limit how quickly we can travel through space. Traditional chemical rockets, while effective for getting us into orbit, are not efficient for long distance travel, so scientists are exploring alternative propulsion methods, such as ion drives or nuclear thermal propulsion, which could enable faster travel times. But these technologies are still in development and require extensive testing. Another aspect of technology is the need for reliable navigation systems. In the vastness of space, pinpointing a location is far more complicated than on Earth, and existing GPS systems do not work beyond our planet, meaning spacecraft must rely on star tracking and other methods through the galaxy. Additionally, the psychological and physical effects developing nuclear fusion engines for spacecraft presents a host of significant technical challenges, each one critical to the feasibility and safety of such advanced technologies. One of the primary challenges lies in achieving the necessary conditions for nuclear fusion to occur, which requires extremely high temperatures, often exceeding millions of degrees Celsius. Maintaining such temperatures, while also containing the fusion reaction, is no small feat, as it necessitates advanced magnetic confinement systems, like those found in tokamaks, or inertial confinement methods, which use lasers to compress fuel pellets. Another major hurdle is the development of materials that can withstand the intense heat and radiation produced during fusion reactions, as most materials would degrade rapidly under such extreme conditions, leading to potential failures in spacecraft systems. In addition, the fuel for nuclear fusion, typically isotopes of hydrogen like deuterium and tritium, must be sourced and handled with great care, as tritium is radioactive and has to be bred in the reactor itself, adding another layer of complexity to the design and operation of fusion engine. The efficiency of the fusion process is also a concern. Researchers must develop methods to sustain a net positive energy output, which means generating more energy from the fusion reaction than is consumed in achieving and maintaining the reaction itself. This is often referred to as achieving ignition, and it's a crucial milestone for any practical fusion engine. Moreover, there are significant engineering challenges related to the integration of fusion systems into spacecraft designs. The reactors must be compact enough to fit within the limited space of a spacecraft, yet powerful enough to provide the thrust necessary for interstellar travel. This requires innovative design solutions to balance power output, size and weight, which are all essential for effective spacecraft operation. Furthermore, the cooling systems needed to manage the heat generated during fusion are complex and must be reliable, as overheating could lead to catastrophic failures. Safety is another paramount concern, as the operation of a nuclear fusion engine must ensure that no harmful radiation escapes into the spacecraft or the surrounding environment. Developing effective shielding that can protect both crew and electronics from radiation while maintaining the efficiency of the engine is a complex task. Additionally, there are challenges surrounding the regulatory and public acceptance of nuclear technologies in space, which can affect funding, research and development timelines. Finally, there are economic challenges related to the development and deployment of nuclear fusion and nuclear fusion engines. The research and technology needed to make fusion engines practical are costly and require sustained investment over many years. This includes not only the technological advancements, but also the infrastructure safety concerns regarding nuclear reactions play a significant role in shaping the direction and pace of fusion propulsion research, which is a burgeoning field that holds promise for future space travel. While traditional nuclear fission reactors, such as those used in power plants and naval vessels, have established protocols and safety measures, fusion propulsion presents a different set of challenges and considerations. Fusion, the process that powers the sun, involves fusing light atomic nuclei, like hydrogen isotopes, to create energy, which is a fundamentally different mechanism compared to fission, where heavy nuclei are split. One of the primary safety concerns in fusion propulsion research revolves around the potential for uncontrolled reactions. Although fusion reactions require extremely high temperatures and pressures to occur, researchers are still investigating how to ensure that these conditions are maintained safely, especially in a spacecraft environment where human lives are at stake. The possibility of a runaway reaction, while much lower in fusion compared to fission, still requires careful design and engineering to prevent any catastrophic failures. Additionally, the materials used in fusion reactors must withstand extreme conditions, including intense heat and radiation, which raises concerns about the long-term integrity of spacecraft components and the safety of the crew on board. Moreover, the handling and storage of fusion fuels, which often include isotopes like deuterium and tritium. Also, tritium, for example, is radioactive, and while it has a relatively short half-life, any potential leaks or mishandling could pose risks to both the crew and the environment. As a result, researchers must develop robust containment and safety systems, thus impacting the design and feasibility of fusion propulsion systems. The regulatory landscape is another factor influencing propulsion research, as governments and space agencies consider the implications of using nuclear technology in space. They must also address the safety protocols that govern such activities. This involves collaboration with regulatory bodies to establish guidelines that ensure the safe development and potential deployment of fusion propulsion systems. Furthermore, public perception of nuclear technology can influence funding and support for fusion research. Safety concerns often lead to skepticism about nuclear power in general, and this skepticism can affect political and financial backing for fusion propulsion initiatives. Scientists and engineers in this field must work diligently to communicate the safety measures, advancements, and potential benefits of fusion propulsion, helping to shift public opinion and garner the necessary support for further research. In addition, as the technology progresses, lessons learned from past nuclear accidents, whether in fission reactors or other contexts, inform the safety protocols and engineering practices adopted in fusion-developing fusion propulsion technology brings with it a variety of considerations which are pivotal in determining its feasibility and potential impact on space exploration and beyond. First, the initial investment required for research and development is substantial, as creating a working fusion propulsion system involves cutting-edge technology, complex engineering, and extensive testing, which can lead to costs running into billions of dollars. This funding must often come from a combination of government sources, private investors, and partnerships with aerospace companies, all of whom seek to understand the potential returns on their investments, given the long timelines and inherent risks involved. Moreover, the economic viability of fusion propulsion hinges on the operational costs associated with maintaining and running fusion reactors. Unlike conventional chemical rockets, which rely on fuel that can be costly and finite, fusion propulsion promises to utilize abundant resources such as deuterium and helium, 3 isotopes of hydrogen that are found in seawater and the moon, respectively. This could lead to lower fuel costs in the long run, but the technology must first prove that it can produce energy efficiently and reliably, which is a significant hurdle. The potential for fusion propulsion extends beyond merely reducing costs for launching payloads. It could also revolutionize travel within our solar system, making missions to Mars, asteroids, and even the outer planets more feasible and cost-effective. If successful, this could open up new markets for space exploration, including mining asteroids for resources which could generate a substantial economic return. Furthermore, improved propulsion technology could shorten travel times, which would enhance the safety and feasibility of long-duration missions, potentially leading to increased investments in space by both governments and private sectors. On the flip side, there are economic risks associated with investing in fusion propulsion technology. The long timelines for development, coupled with the technical challenges that still need to be overcome, mean that investors may face uncertainties about the ultimate success of the technology. Additionally, competition from other propulsion technologies, such as ion drives or solar sails, could impact the market viability of fusion propulsion, as these alternatives may require less investment and offer quicker returns. Another key consideration is the regulatory landscape surrounding nuclear technology. Fusion propulsion systems will likely face stringent regulations and safety concerns, which could add to development costs and create additional hurdles for market entry. This regulatory environment will need to evolve to accommodate such innovations, ensuring that safety measures are in place while also fostering an environment conducive to technological advancement. Moreover, the potential societal benefits of fusion propulsion, such as enabling humanity's expansion into space, when we think about design concepts in the context of space exploration and astronomy, it's fascinating to see how these ideas have evolved over time, reflecting our growing understanding of the universe. One notable design concept is the idea of modular spacecraft, which allows for different components to be added or removed depending on the mission's needs. This approach not only maximizes efficiency, but also allows for greater flexibility in mission planning. For instance, NASA's Orion spacecraft, designed for deep space missions, incorporates a modular design that can be adapted for various objectives, whether it's crewed missions to the Moon or Mars, or even beyond. Another interesting design concept is the use of inflatable habitats for astronauts, which could revolutionize how we think about living in space. These habitats are lightweight, compact, and can be deployed quickly, making them ideal for missions to places like Mars, where building permanent structures may take years or even decades. Companies like Bigelow Aerospace are already experimenting with inflatable modules, which provide the necessary living space for astronauts while being easy to transport and set up. Then there's the concept of regenerative life support systems, which is crucial for long-duration space missions. This design focuses on creating closed-loop systems that recycle air, water, and waste by using plants and other biological processes. These systems can sustain human life for extended periods, reducing the need to transport supplies from Earth. Research from organizations like ESA has shown promising results, with experiments carried out on the International Space Station, demonstrating how plants can thrive in microgravity and contribute to life support. Additionally, the design of spacecraft is also heavily influenced by the challenges of radiation exposure in space. Designers are now integrating materials and technologies that can provide better shielding from cosmic rays and solar radiation. For example, researchers are exploring the use of polyethylene, which is known for its effectiveness in blocking radiation, as a primary material for spacecraft walls, especially for missions beyond low Earth orbit. Moreover, the design of space telescopes has dramatically changed our understanding of the universe. The Hubble Space Telescope, launched in 1990, has been a groundbreaking example of how design can enhance our ability to observe distant galaxies, nebulae, and exoplanets. The design considerations for Hubble included its location above the Earth's atmosphere, which allows for clearer images, as well as its modularity, enabling servicing missions that have kept it operational for years longer than originally planned. In addition, the concept of swarm robotics is gaining traction in space exploration. This design idea, in the quest for advanced space travel, scientists and engineers have proposed several fascinating designs for fusion. Powered spacecraft aiming to harness the immense energy produced by nuclear fusion, the same process that powers the stars, including our sun. One of the most talked about concepts is the fusion rocket, which could utilize fusion reactions to propel a spacecraft through space at incredible speeds. This design often envisions a system where a fusion reaction creates high-energy plasma, which is then expelled at high velocities through a nozzle, generating thrust. Theoretical designs like the direct fusion drive are particularly noteworthy, as they combine elements of both fusion and electric propulsion, potentially allowing for efficient travel to distant destinations, such as Mars, or even beyond. Another captivating concept is the use of inertial confinement fusion, where small pellets of fuel are compressed and heated to the point of fusion using powerful lasers. This could lead to a spacecraft that fires bursts of energy to produce thrust, allowing for rapid acceleration and deceleration, which is crucial for space missions. The National Ignition Facility in the United States has been a pioneer in this area, conducting experiments that could inform future spacecraft designs. Additionally, there are designs that incorporate magnetic confinement fusion, where magnetic fields are used to contain the hot plasma produced during fusion reactions. This type of spacecraft would utilize advanced superconducting magnets to create a magnetic field strong enough to keep the plasma contained, ensuring the reaction continues efficiently, while also providing the means to convert the fusion energy into usable thrust. The concept of a magnetoplasma dynamic engine represents this approach, which could potentially offer a continuous thrust, allowing for long-duration missions without the need for large amounts of fuel. Moreover, researchers have considered more exotic ideas, such as the use of fusion-powered sails, which would utilize the energy produced by fusion reactions to propel a spacecraft using the pressure from emitted particles or radiation. This design could enable spacecraft to travel vast distances without the need to carry heavy fuel supplies, relying instead on the energy generated by the fusion process itself. A particularly intriguing proposal comes from the Project Orion concept, which, while initially focused on nuclear fission, has inspired ideas for fusion propulsion. The basic premise involves using directed energy from fusion explosions to propel a spacecraft forward, creating a unique mechanism for thrust. Although this concept raises significant safety and engineering challenges, its potential for rapid interplanetary travel captures the imagination of many in the space exploration community. As we look to the future, the promise of fusion-powered spacecraft represents not only a leap integrating a fusion engine into a spacecraft's overall design, involves several complex considerations, as fusion propulsion represents a significant leap from conventional chemical rockets. First, the spacecraft's structure must accommodate the fusion reactor, which, unlike traditional engines, requires a robust containment system to manage the extreme conditions of a fusion reaction. This containment typically involves magnetic fields or inertial confinement methods. So the design would need to include strong magnets and advanced materials that can withstand intense heat and radiation. The weight and size of the fusion engine compared to chemical engines would also be a factor. Fusion engines could be heavier, but they offer much greater efficiency. So the overall design may be streamlined to optimize for this. Moreover, the craft's thermal management systems must be enhanced to handle the heat generated by the fusion process. So integrating radiators or heat exchangers into the exterior design would be essential. The propulsion system would need to be connected to the spacecraft's power systems, as fusion engines generate electricity, which can be utilized to power onboard systems, instruments, or even to provide additional thrust through electric propulsion methods. The integration of the fuel supply for fusion, which typically involves isotopes like deuterium and tritium, also presents challenges. Storage tanks must be designed with safety in mind, and they need to be incorporated into the spacecraft's layout efficiently. In addition, the cockpit and control systems would require modifications to handle the unique operational characteristics of fusion propulsion, including monitoring the reactor's stability and adjusting the fusion output for thrust. This means that the interface for pilots or automated systems would need to be developed with new telemetry and control algorithms. Furthermore, the spacecraft's trajectory planning would take into account the different thrust profiles of fusion engines, which can provide continuous thrust over long periods, allowing for more efficient travel to distant destinations such as Mars or even the outer planets. Additionally, safety protocols must be established, as the fusion engine poses different risks compared to traditional engines. Engineers would need to design fail-safes and emergency systems to prevent radiation leaks or reactor malfunctions. Finally, the integration of a fusion engine would also have implications for the spacecraft's mission profile, potentially allowing for missions that previously seemed impractical due to time constraints, opening new avenues for exploration in our solar system and beyond. Superconductors are playing a crucial role in the development of fusion propulsion systems, which are seen as a potential game changer for space travel, allowing for faster and more efficient journeys through our solar system and beyond. At the heart of fusion propulsion is the idea of harnessing the power of nuclear fusion, the same process that fuels the stars, including our Sun, where light atomic nuclei combine to form heavier nuclei, releasing immense amounts of energy in the process. This energy could be used to propel spacecraft, allowing them to travel at a significant fraction of the speed of light, which is far beyond what is currently possible with chemical rockets. Now, superconductors, which are materials that can conduct electricity without any resistance when cooled to very low temperatures, offer several advantages for fusion propulsion systems. For one, they can create very strong magnetic fields that are essential for containing and controlling the hot plasma needed for nuclear fusion. In a fusion reactor, the plasma must be kept stable and confined away from the walls of the reactor vessel. And this is where superconducting magnets come into play, as they can generate the strong magnetic fields necessary for this confinement, without wasting energy, unlike traditional magnets, which lose energy due to resistance. In addition to providing efficient magnetic confinement, superconductors can also help improve the overall efficiency of fusion propulsion systems. The ability to generate powerful magnetic fields without energy loss means that more of the energy produced from fusion can be converted into thrust, making the propulsion system more effective. This is particularly important in space travel, where every ounce of thrust counts and efficiency translates to longer missions and the ability to carry more payload. Researchers are actively exploring materials that can become superconducting at higher temperatures, which would make them easier to use in practical applications, including space missions. Current superconductors require cooling with liquid helium, which adds complexity and weight to any system. However, if high-temperature superconductors can be developed and utilized, it could revolutionize the design and feasibility of fusion propulsion systems, allowing for lighter spacecraft and more straightforward cooling systems. Moreover, the development of fusion propulsion systems powered by superconductors could lead to breakthroughs in long-duration space missions, such as manned missions to Mars or even beyond to the outer planets and their moons. The combination of high efficiency and the ability to sustain thrust for extended periods could significantly reduce travel times, making interplanetary travel more practical and opening up new possibilities for exploration of our solar system. Overall, superconductors are an integral part of the ongoing when we think about the vastness of space. One interesting aspect that often comes to mind is how we test and implement new technologies for space exploration, as these processes are critical to ensuring the success of our planet. Testing in space exploration typically involves a series of rigorous evaluations, as engineers and scientists must simulate the conditions of space on Earth, which can be incredibly challenging given the extreme environments encountered beyond our atmosphere, with temperatures that can plunge to nearly absolute zero, and radiation levels that can be harmful to both equipment and humans. One common method of testing is the use of vacuum chambers, where scientists can recreate the vacuum of space, allowing them to observe how materials and instruments behave without the influence of air pressure. Additionally, thermal vacuum tests are conducted to assess how spacecraft systems will handle the extreme temperature fluctuations of space, moving from the intense heat of direct sunlight to the frigid cold of shadowed areas, which can vary drastically in a single orbit around Earth. Moreover, testing does not stop on the ground. Once a spacecraft is launched, it undergoes further evaluations during its journey. For example, the Mars rovers are equipped with numerous sensors that continuously monitor their systems, sending data back to mission control, which helps engineers make adjustments or troubleshoot any issues that arise. This real-time data collection is crucial, as it allows for immediate responses to unexpected challenges, which are common in the unpredictable environment of space. Implementing new technologies often involves collaboration between various organizations, including government space agencies like NASA, private companies, and international partners, which can lead to innovations that push the boundaries of what we can achieve in space exploration. For instance, The development of reusable rocket technology has significantly reduced costs and increased access to space, allowing for more frequent missions and a greater variety of experiments to be conducted. Another fascinating aspect is how testing leads to the implementation of life support systems, which are essential for human spaceflight. These systems must be meticulously designed, tested, and validated to ensure that astronauts have a safe and habitable environment while in space. This includes everything from oxygen generation and carbon dioxide removal to water recycling and temperature control, all of which must function flawlessly in the harsh environment of space. The International Space Station serves as a prime example of this, where ongoing research helps improve life support technologies, not just for current missions, but also for future endeavors, such as manned missions to Mars. In addition, one of the most critical factors in testing and implementation is the importance of redundancy, testing fusion propulsion systems on Earth before taking them into the vastness of space involves a complex interplay of scientific experimentation considerations. To begin with, scientists can utilize specialized facilities, known as fusion test reactors, which mimic the conditions necessary for nuclear fusion to occur. These reactors, like the ITER project in France, are designed to create and control plasma, the hot, charged state of matter where fusion reactions can occur. Researchers can conduct various experiments to understand the behavior of this plasma, how to contain it, and how to contain it, and how to harness the energy produced for propulsion. Addition to large-scale facilities, smaller experimental setups can be used, allowing for more controlled tests of different fusion propulsion concepts. These smaller facilities can focus on specific components of the propulsion system, such as the magnetic confinement method, where powerful magnetic fields are employed to keep the hot plasma stable, or inertial confinement, which uses lasers to compress and heat fusion. Each of these methods offers unique insights into how fusion can be effectively harnessed for propulsion. Moreover, computer simulations and advanced modeling techniques play a crucial role in testing fusion propulsion systems. By simulating various scenarios, scientists can predict how these systems will perform under different conditions, identify potential issues, and optimize designs. These simulations can help determine the best materials for construction, the most efficient fuel types to use, and the overall design of the propulsion system, which is vital before any physical testing occurs. Conducting experiments on Earth also involves rigorous safety protocols. Given that fusion reactions, while not as hazardous as fission reactions, still produce high energy particles and radiation, researchers must ensure that all safety measures are in place to protect personnel and the environment. This includes creating containment structures using remote handling techniques and ensuring that any radioactive materials are properly managed. The development of subscale models, which are smaller, less powerful versions of the intended fusion propulsion system, allows for hands, on testing without the full risks associated with a full-scale system. These models can be tested in various environments to study their performance, durability and efficiency in a controlled setting. The data collected from these tests are essential for refining the designs and making necessary adjustments before moving forward to larger, more complex systems. Collaboration with international space agencies and research institutions can also enhance the testing process. By pooling resources, knowledge and expertise, scientists can conduct joint experiments, share findings, and accelerate the development of viable fusion propulsion technologies. This global effort is crucial, as when discussing the criteria for a successful fusion propulsion system, it's essential to understand the fundamental principles behind fusion energy itself, which is the process that powers stars, including our Sun. A successful fusion propulsion system should meet several key criteria. The first being the ability to achieve and maintain the necessary temperatures for fusion reactions to occur. These temperatures are typically in the range of millions of degrees Celsius, far exceeding what conventional chemical propulsion systems can achieve. This means that the system must incorporate advanced heating methods, such as magnetic confinement or inertial confinement, to create and sustain the extreme conditions needed for fusion. Another important criterion is the confinement time, which refers to how long the fusion fuel can be kept at the high temperatures and pressures required for the reaction to occur. The longer the confinement time, the more likely it is that the fusion fuel will undergo reactions, producing energy. To achieve this, the system must utilize innovative containment strategies, such as powerful magnetic fields, to prevent the hot plasma from coming into contact with the walls of the containment vessel, which could cool it down and halt the fusion process. Efficiency is also a critical factor, as a successful fusion propulsion system must convert a significant portion of the fusion energy released into thrust. This requires the development of advanced energy conversion technologies, which can transform the energy produced by fusion reactions into usable propulsion power. For instance, this could involve using the high-energy neutrons produced in fusion reactions to heat a working fluid, which would then be expelled to generate thrust. Additionally, the design of the fusion propulsion system should prioritize safety and reliability. Fusion reactions, while generally considered safer than fission reactions, still pose challenges, such as the management of radioactive materials and the potential for equipment failure under extreme conditions. Therefore, the materials used in the construction of the system must be able to withstand high temperatures, radiation, and other stresses associated with fusion reactions. Another criterion is the scalability of the system, meaning that it should be feasible to adapt the technology for various applications, from powering spacecraft for deep space missions to potentially providing energy for bases on other planets. This scalability requires a modular design, allowing for adjustments in size and power output depending on the mission needs. Cost effectiveness cannot be overlooked either, as developing a fusion propulsion system involves significant initial investment, and the technology must be economically viable compared to existing propulsion systems. This involves not only the cost of materials and construction, but also the long-term operational costs associated with running the system. Lastly, the overall technological readiness. When it comes to testing procedures for fusion propulsion, the approach is quite different from that of traditional propulsion systems, primarily due to the unique principles and technologies involved in fusion. Traditional propulsion systems, such as chemical rockets, rely on the combustion of fuel to produce thrust, which is a well-understood process. The testing of these systems often includes static fire tests, where the engine is fired while secured to a test stand, allowing engineers to measure thrust, temperature, and other performance metrics. In contrast, fusion propulsion systems, which aim to harness the energy produced by nuclear fusion reactions, require a very different set of testing protocols. First, the testing environment for fusion propulsion must be designed to handle extreme conditions, including high temperatures and pressures that are not typically encountered in chemical propulsion tests. Fusion reactions produce energy by fusing atomic nuclei, which necessitates the creation of conditions similar to those found in stars, specifically the high-energy plasma state. Thus, the test facilities must incorporate specialized equipment to generate and contain this plasma, using magnetic confinement or inertial confinement techniques. In traditional propulsion, the focus is primarily on the fuel and the combustion chamber. However, for fusion propulsion, the entire system must be engineered to manage plasma behavior, stability, and confinement, which adds complexity to the testing procedures. Moreover, the operational parameters for fusion propulsion systems are vastly different. Traditional systems operate on a straightforward fuel cycle, where the fuel is consumed in a predictable manner. Fusion propulsion, however, involves advanced technologies that must be thoroughly understood and tested, including the fusion fuel itself, often isotopes like deuterium and tritium, which are far less common than the kerosene or liquid oxygen used in conventional rockets. Testing fusion propulsion systems will likely involve a series of incremental tests to evaluate the fusion reactions, starting with small-scale experiments to study the behavior of plasma under controlled conditions, before moving on to larger, more complex tests that simulate actual flight scenarios. Another key aspect is the measurement of thrust and efficiency in fusion propulsion, which is not as straightforward as in traditional systems. In chemical propulsion, thrust can be measured directly through the force produced during the combustion process. In fusion propulsion, however, the thrust is generated by the expulsion of high-energy particles, and the methods for accurately measuring this thrust must be developed and validated. This might involve sophisticated diagnostic tools, such as laser interferometers or high-speed cameras, to capture the dynamics of the plasma and the resultant thrust vector. Safety testing is also, in recent years, The applications of technology in space exploration have expanded dramatically, affecting not just how we explore, but also what we can learn from the cosmos. One of the most fascinating advancements is the use of artificial intelligence, which is now being employed to analyze vast amounts of data collected from space missions. For example, NASA's Mars rover, Perseverance, uses AI to navigate the Martian terrain autonomously, making decisions about which paths to take and which samples to collect, thus enhancing the efficiency of exploration on the Red Planet. This capability is crucial, as it allows scientists to focus on analyzing the data rather than managing the rover's every movement, ultimately speeding up our understanding of Martian geology and potential signs of past life. Moreover, satellite technology has revolutionized our ability to monitor Earth and other celestial bodies. Satellites equipped with advanced sensors can provide real-time data about weather patterns, climate change, and even deforestation on our own planet. When we look beyond Earth, satellites play a key role in planetary exploration, gathering crucial information about the atmospheres and surfaces of distant planets and moons. For instance, the Hubble Space Telescope has given us breathtaking images and insights into the formation of galaxies, stars, and planetary systems, contributing immensely to our understanding of the universe's evolution. In addition to AI and satellite technology, robotics has also made significant contributions to space exploration. Robotic missions, such as the Voyager spacecraft, have traveled beyond our solar system, sending back data about the outer planets and even interstellar space. These robots can withstand the harsh conditions of space, reaching places where human explorers cannot go, and they continue to provide invaluable information about the cosmos. The recent success of the Perseverance rover, which not only carries scientific instruments but also a helicopter called Ingenuity, highlights how robotics can enhance exploration by enabling aerial surveys of Mars, offering a new perspective that ground-based rovers cannot achieve. Another exciting application is the use of 3D printing technology in space. This innovation is paving the way for building structures and tools in space, rather than launching everything from Earth. NASA has been experimenting with 3D printing to create parts and even entire habitats that could support astronauts on long-duration missions like those to Mars. This approach reduces the need for heavy launches and allows for more sustainable practices in space exploration, as it utilizes local materials, which may be available on other planets or moons. Furthermore, the development of reusable rocket technology has changed the economics of nuclear fusion propulsion technology holds immense potential for future space exploration missions, as it promises to provide much greater efficiency and speed compared to conventional chemical rockets. One of the most significant missions that could benefit from this technology is a crewed mission to Mars, which has been a focus of space agencies like NASA and private companies like SpaceX. With nuclear fusion propulsion, spacecraft could achieve faster travel times, reducing the time astronauts would spend in space. thus minimizing their exposure to harmful cosmic radiation and the psychological challenges of long-duration missions. Additionally, missions aimed at exploring the outer planets, such as Jupiter and Saturn, could also gain from fusion propulsion. The distances to these planets are vast, and traditional propulsion methods would require years of travel, whereas fusion technology could shorten the journey significantly, allowing for more extensive exploration and possibly even human landings on icy moons like Europa or Titan. Believed to harbor subsurface oceans and could be prime candidates for finding extraterrestrial life. Another exciting possibility is the concept of interstellar missions, which have long been a dream for scientists and enthusiasts alike. Proposals for missions to nearby star systems, such as Alpha Centauri, suggest that fusion propulsion could make such journeys feasible within a human lifetime, unlike the slow, decades-long trips that current technology would impose. With fusion, spacecraft could potentially reach speeds a significant fraction of the speed of light, allowing us to send probes or even crewed missions to explore the stars, gathering data about exoplanets and searching for signs of life. Moreover, lunar missions could also see enhancements from nuclear fusion technology, especially with plans to establish a sustainable human presence on the Moon. Fusion propulsion could facilitate more efficient transportation of materials and personnel to and from lunar bases, supporting construction and research efforts, as we aim to utilize the Moon as a stepping stone for deeper space exploration. In addition, fusion propulsion might revolutionize satellite deployment and maintenance in Earth's orbit. The ability to launch and reposition satellites more efficiently could lead to advances in telecommunications, Earth observation, and space science, as satellites could be placed in more optimal orbits or even taken on missions to nearby asteroids for resource extraction. Lastly, missions to asteroids, which are considered valuable for their mineral resources, could also benefit significantly from fusion propulsion. Fast and efficient travel to and from these celestial bodies would enable more ambitious mining operations, as well as scientific studies of their composition and history, which could provide insights into the early solar system. In conclusion, nuclear fusion propulsion, which harnesses the energy produced by nuclear fusion reactions, could revolutionize space travel, particularly for crewed missions to Mars and beyond, offering several significant advantages over conventional propulsion systems. Unlike chemical rockets that burn fuel and produce thrust through combustion, fusion propulsion generates energy by fusing light atomic nuclei, like hydrogen isotopes, into heavier elements, releasing vast amounts of energy in the process. This method could lead to much higher efficiency, allowing spacecraft to achieve greater speeds without the massive amounts of fuel required by traditional methods. Imagine a spacecraft using fusion propulsion. It could reach Mars in as little as 30 days, compared to the typical 6 to 9 months needed with current technology. This remarkable reduction in travel time not only makes missions more feasible, but also significantly decreases the exposure of astronauts to harmful space radiation and microgravity effects. The ability to travel faster also opens up the possibility of crewed missions to outer planets, such as Jupiter or Saturn and their moons, where the potential for exploration and discovery is immense. Additionally, fusion propulsion systems could provide continuous thrust, allowing for smoother acceleration and deceleration, which is particularly important for crew comfort and safety during long-duration flights. By gradually increasing speed, astronauts would experience less stress on their bodies, reducing the risk of health issues associated with sudden changes in velocity. Furthermore, the energy produced through fusion could be utilized not just for propulsion, but also to power life support systems and other onboard technologies, enhancing the self-sufficiency of the spacecraft during its journey. Moreover, since fusion fuel such as deuterium and tritium can be sourced from water and lithium, which are abundant on Earth and possibly on other celestial bodies, this opens up exciting possibilities for in situ resource utilization. Future missions could potentially refuel on Mars or on asteroids, making deep space exploration more sustainable and practical. The technology for fusion propulsion is still in its early developmental stages, requiring advancements in plasma confinement and stability to create a practical engine for space travel. However, projects like the International Thermonuclear Experimental Reactor, ITER, and various private initiatives are making strides toward harnessing fusion energy, which could eventually lead to the development of fusion-powered spacecraft. As research continues, the prospect of fusion propulsion promises not only to make crewed missions to Mars and beyond a reality, but also to transform our understanding of the universe, enabling human presence in previously unreachable realms of space. The quest for fusion propulsion encapsulates the spirit of exploration and fusion propulsion. A concept that harnesses the power of nuclear fusion could revolutionize deep space exploration by providing a highly efficient means of propulsion, allowing spacecraft to travel faster and farther than ever before. Unlike conventional chemical rockets, which rely on the combustion of fuel and produce limited thrust, fusion propulsion systems could generate thrust by fusing light atomic nuclei, such as hydrogen isotopes, into heavier elements, releasing vast amounts of energy in the process. This energy could be used to accelerate a spacecraft to a significant fraction of the speed of light, enabling missions that reach other star systems within a human lifetime, a feat currently thought impossible with existing technology. Imagine a spacecraft powered by fusion traveling at speeds of up to 10% the speed of light. This could allow for missions to nearby stars, like Proxima Centauri, in just over 40 years, rather than the thousands of years it would take with traditional propulsion methods. Additionally, fusion propulsion could allow for continuous thrust, which is a game-changer in the realm of space travel. Instead of burning fuel in short bursts as traditional rockets do, A fusion engine could provide a steady stream of thrust, significantly reducing travel time to far-off destination. This capability could open the door to exploring the outer planets of our solar system and beyond, including missions to the Kuiper Belt and even the Oort cloud, where many comets and potential resources reside. The ability to explore these distant regions could lead to new discoveries about the formation of our solar system and the potential for resources that could support long-term human habitation in space. Furthermore, fusion propulsion could enable the use of in-situ resource utilization, where spacecraft could gather materials from asteroids, moons, or even planets, and use them to create fuel for their return journey or for further exploration. This would reduce the amount of fuel that needs to be launched from Earth, making deep space missions more sustainable and cost-effective. If we could establish a network of fusion-powered spacecraft, each capable of exploring different regions of space, we could gather data and samples from a vast area of the cosmos, significantly enhancing our understanding of the universe. The safety of crew members could also see major improvements with fusion propulsion. Traditional chemical rockets involve the risk of explosions and other hazards associated with fuel combustion. Fusion, on the other hand, has the potential to be a much safer method of propulsion, as the conditions needed for the fusion reaction to occur require precise control. While there are technical challenges to developing a practical fusion propulsion system, in recent years, the exploration of space has raised important environmental and ethical considerations as humanity's quest to reach beyond our planet encounters new challenges. One of the primary concerns revolves around the potential for space debris, which is a growing issue as more satellites and spacecraft are launched into orbit. With thousands of defunct satellites, spent rocket stages and fragments from collisions, the risk of creating a cascade of debris, often referred to as the Kessler syndrome, becomes increasingly plausible. This scenario poses a threat to minimize the ecological footprint of space travel. The production of these rockets often involves significant energy consumption and the depletion of natural resources, raising questions about the sustainability of our endeavors in space. Ethically, the question of space colonization also invites debate. As we consider sending humans to Mars or establishing bases on the Moon, we must think about the implications for any existing ecosystems, even if they are not as familiar. For instance, if microbial life exists on Mars, how do we ensure we do not contaminate it with Earth-based organisms? The planetary protection protocols are designed to prevent this, but the balance between exploration and preservation is delicate and complex, requiring careful consideration from scientists, ethicists, and policymakers alike. Moreover, the commercialization of space raises ethical dilemmas about who gets to benefit from these resources. As private companies venture into space mining, particularly for asteroids rich in metals and minerals, the question arises, who owns these? International space law, primarily governed by treaties such as the Outer Space Treaty of 1967, asserts that space is the province of all humankind. Yet the rapid advancement of technology and private enterprise complicates this principle. The potential for exploitation of space resources could lead to conflicts over ownership and usage, echoing historical patterns seen in resource-rich regions on Earth. Furthermore, the societal implications of space exploration extend to considerations of equity and access. As nations invest in space programs, disparities in funding and capabilities may lead to a divide between those who can afford to explore and those who cannot. This raises the question of whether the environmental implications of using nuclear fusion in space are a fascinating topic, as fusion could represent a significant shift in how we approach energy in the cosmos. Unlike nuclear fission, which splits heavy atoms and produces long-lived radioactive waste, nuclear fusion involves combining light atomic nuclei, such as hydrogen isotopes, to form helium, releasing immense amounts of energy in the process. This reaction is similar to the processes that power the sun, which means, if harnessed correctly, fusion could provide a virtually limitless source of energy, with the primary byproduct being helium, a harmless gas. One of the most compelling environmental benefits of fusion is its potential for reducing the carbon footprint of space missions. Traditional rocket propulsion systems often rely on fossil fuels or other chemical propellants, which can produce significant greenhouse gas emissions. If fusion technology can be successfully developed for space travel, it could allow spacecraft to operate with a much lower environmental impact, as the energy produced from fusion would not contribute to atmospheric pollution or climate change. Additionally, fusion fuel, particularly deuterium and tritium, can be sourced from seawater and lithium, both of which are abundant. This means that for long-duration space missions, such as those planned for Mars or beyond, the environmental impact of resource extraction, using resources from celestial bodies like asteroids or the Moon, could further reduce the need to launch large amounts of fuel from Earth, thus decreasing the overall ecological footprint of space exploration. However, it is also essential to consider the potential risks associated with developing nuclear fusion technology for space applications. The construction and operation of fusion reactors could pose challenges in terms of safety, particularly in avoiding any form of radiation leaks or accidental releases in the vacuum of space. While fusion produces much less radioactive waste than fission, there remains the need to ensure that any materials used in the reactors do not become hazardous or contribute to space debris. Moreover, the technology for practical nuclear fusion is still in developmental stages, and while scientists are optimistic, it may take decades before fusion becomes a viable energy source for space. The environmental implications of pursuing this technology are substantial, as the research and development phase could lead to other innovations, possibly yielding cleaner energy solutions that could benefit life on Earth as well. In summary, while nuclear fusion holds remarkable promise for reducing the environmental impact of space exploration, careful consideration of its risks, resource acquisition, and technological development is crucial in ensuring that this potential is realized in a sustainable and responsible manner. The use of nuclear technology in space exploration certainly raises important ethical concerns, especially when considering its potential risks and benefits to both humanity and the environment. Nuclear propulsion systems, for example, could greatly enhance our ability to explore distant planets and moons, offering much faster travel times than conventional chemical rockets. However, the deployment of such technologies comes with significant worries about safety, particularly in the event of a launch failure or an accident during operation. If a spacecraft powered by nuclear technology were to crash, it could potentially release radioactive materials into the atmosphere, creating long-lasting environmental damage and posing serious health risks to people and wildlife. Furthermore, there are concerns about the long-term implications of using nuclear power in space. The potential contamination of celestial bodies, particularly those that might host life, poses a moral dilemma. When sending missions to places like Mars or Europa, scientists must consider whether introducing nuclear technology might interfere with existing ecosystems or contaminate pristine environments, thus hampering our ability to study them in their natural state. This raises questions about our responsibility as explorers and whether we should prioritize scientific curiosity over the preservation of these worlds. Another ethical issue stems from the governance of nuclear technology in space. The Outer Space Treaty of 1967, which has been signed by many countries, including major spacefaring nations, prohibits the placement of nuclear weapons in space and emphasizes that space exploration should be conducted for the benefit of all humanity. However, the interpretation and enforcement of this treaty can be complicated, especially when it comes to the use of nuclear materials for peaceful purposes, such as powering spacecraft. The potential militarization of space, driven by advancements in nuclear technology, could lead to geopolitical tensions, and ethical questions about the ownership and use of space resources arise. Moreover, there are societal implications to consider, as the public perception of nuclear technology can be quite polarized. Many people associate nuclear power with disasters, such as Chernobyl and Fukushima, leading to fear and distrust regarding its application in space exploration. This societal skepticism can influence funding for research and development, as well as public support for missions that utilize nuclear technology. Scientists and policymakers must navigate these concerns carefully, ensuring that they communicate the benefits and risks transparently to foster informed public discourse. Lastly, the issue of intergenerational ethics comes into play, as the decisions made today regarding the use of nuclear technology in space exploration will have lasting impacts on future generations. The long-lived isotopes used in nuclear reactors could remain hazardous for thousands of years, which raises when we discuss the waste produced by fusion compared to that produced by fission. It's important to first understand the fundamental differences between these two nuclear processes. Fusion, which is the process that powers the Sun and other stars, involves the merging of light atomic nuclei, such as hydrogen isotopes, to form heavier nuclei, releasing a significant amount of energy in the process. In contrast, fission involves splitting heavy atomic nuclei, such as uranium or plutonium, into lighter elements, also releasing energy. The waste produced by these processes is a crucial consideration, especially when evaluating their environmental impact and long-term viability as energy sources. Fusion produces very little waste, primarily because the main fuel used in fusion reactions, like deuterium and tritium, are isotopes of hydrogen. The byproducts of fusion are typically helium and some neutrons. Helium is a harmless gas that poses no environmental threat. The neutrons produced can interact with surrounding materials, but these interactions are usually manageable. The neutron activation can create some radioactive materials, but fusion reactors are designed to minimize this waste, and the radioactivity of any resulting materials tends to be short-lived. This means that the long-term storage and disposal of fusion waste would be significantly less complicated compared to fission. On the other hand, fission produces a variety of radioactive isotopes, many of which are highly toxic and have long half-lives, meaning they remain hazardous for thousands of years. The waste from fission includes isotopes like cesium, 137, and strontium, 90, which are products of the fission process, as well as actinides like plutonium, which can remain dangerous for tens of thousands of years. The management of fission waste is a significant challenge, requiring secure storage solutions, often deep underground, to isolate it from the environment and human populations. This long-term management remains a contentious issue, with debates surrounding the safety and efficacy of current disposal methods. In terms of volume, fusion waste is much smaller, as the reaction produces less waste overall, and the materials that do result from the process are generally less hazardous. This efficiency makes fusion an appealing option for future energy generation, as it could help reduce the burden of waste management associated with nuclear power. Moreover, because fusion fuel can be derived from abundant resources, such as water for deuterium and lithium for tritium, the sustainability of fusion energy is notably higher than that of fission, which relies on finite uranium and plutonium supplies.